All right, so we're going to do limits. I just labeled it 10.1 today. So we're going to go through some definitions and then see how that ends up giving us a limit. So your natural domain here would be if I factored the top and bottom of this and I canceled everything out. So it would first factor in x squared minus 1, x squared plus 1 over 2x minus 1. And then the top again factors and x minus 1, x plus 1. So the x minus 1s would end up canceling, but still would create a hole there if you remember that from Algebra 2 and from this year in pre-calc. So your natural domain would be negative infinity to 0 and 0 to infinity. At 1, it creates, it's undefined there. It really creates a hole. If you remember when you cancel top and bottom, it creates a hole. So as you get really close to 1, so as my x is getting close to 1, my y is getting really close to 2. So you read this as you say, as it approaches. So as x approaches 1, so we're saying if it gets really close. So here's the graph. It's already graphed for you. We want to make some table of values, and I plugged these in my calculator. So when I plugged in 0.9, I got a 1.7195. Oh, I messed up somewhere. This one's supposed to be 2.0003. Somewhere in here I messed it up. 1, 2, 3, 1, 9.02, 1.9, oh, it's 1.97, then 1.9997. So as you can see, x is getting really close to the number 2 on either side. So 1.9997 and 2.003. So it's getting really close to the number of 2. So our notation, we read this right here, is we're saying x is getting close from the left, right? So it's as x approaches from the left side. So that's these numbers right here from the left side. And this is as x approaches from the right side. So that's all of these numbers over here. All right, so that would be coming from the right side. Notation, the limit from the left. So we would say the limit as x approaches 1 from the left of our function. The limit as x approaches 1 from the right of our function. So as we're coming this way, it's getting really, really close to 2. As we're coming from this way, that's the right side, it's still getting really, really close to 2. So this limit does not mean that f of 1 equals 1. It's still undefined there. It just means that our graph gets really close to it. We're getting close to the y value too. So the y values do not have to equal each other. So we're just saying, what's the y getting really close to? So the idea of a limit is what we just said. So as x gets really close to the point, is your y getting close to a point? So you're reading off your y values. So x can never actually equal the a in the real definition, but it's going to become so arbitrarily close that we can't even really tell the difference between them. So we have graphs of these functions right here, and I'm going to teach you how to do these algebraically eventually, but for right now, we're just going to use it on the graph. So to me, it looks like this right here is probably approaching a half. So as x is going to 1, both sides is approaching a half. So right here is x approaches 1. So as x approaches 1 right here, I'm guessing this goes, this is supposed to go by 1s. We're just going to pretend it goes by 1s, because I don't know why else it wouldn't be an asymptote here. So what this is telling me is I approach 1 from the right, I'm going to infinity, and 1 from the left, I'm going to negative infinity. So this one does not exist. So if it was from the left and the right, so I said from the right, we're going to infinity. From the left, we're going to negative infinity. Those aren't the same numbers, so it doesn't exist. For C, here's my graph. So again, the limit from the 0. So this doesn't exist because it's jumping. It's a jump. But if I said 0 from the right, you'd say 1. And 0 from the left, so down here, if it was a plus or minus up there, you would say negative 1. All right, this one right here is oscillating forever and ever and ever and ever. So even though it looks like it might be approaching a number, it actually also does not exist. And that's because it's oscillating forever. And this is like the one function that does that. All right, so now let's look at some graphs and actually try to apply some of the things. So when we're looking here, we're going to say, what's the graph doing from the left and the right? And if it's the same y value, we're going to write it down. So 4 here. So 4 is coming from each direction. I'm going up to 5, down to 5. So my answer is 5. So for 0, from the right side, I'm going up to 2. I'm coming down to 2. So my answer is 2. Even though it's not defined there, it does not matter. Let's go to -2 right here. So as I'm coming down, I'm approaching 3. As I'm going up, I'm approaching 3. So my y value is 3. All right, 3. So from 3, as I'm coming down, as I'm coming to 3, I'm going to 1. But this side, I'm coming to 4. So since these are not the same numbers, the limit does not exist. So let's see, this right here is what it is saying. So 3 from the left is this one down here. So as you're coming from the left side, you're approaching the y value of 1. As you're approaching 3 from the right side, so that's up here. So as you're approaching from the right side, you're going to the y value of 4. So you're looking at y values. So at -4, I'm going up and down, so that does not exist, and we can prove it down here. From the left, I'm going to -infinity. From the right, I'm going to positive infinity. So since those aren't the same numbers, it doesn't exist. As x goes to infinity, it means like what's happening to the graph as we're going to the right. And so to me, it looks like as we're going to the right, it's approaching the line of 6. It might cross the line. They'd probably need to give you more information just to make sure, but I'm going to say 6 for this purpose. And then if we look over here as x goes to -infinity, so as I'm going to the left, the graph looks like it's just going up forever and ever and ever. It doesn't get to approaching anything. So this would be going up to infinity, or you could say D and E, whichever one you're more comfortable with. All right, so properties of limits. So if I know the limit of f of x equals L and g of x equals m, these properties hold. So if I just have a constant as x approaches a, we're still going to get that constant back out. And this one, if I have just a regular x value, so it's going x. So whatever the x is going to be my a value. So this is going to be k times my f's answer. So this is going to be k times the L. It's just saying I can add my two limits. So I'm going to have L plus M. This is saying I can multiply my two limits. So I can multiply them. And this is saying I'm going to divide my two limits. Granted that G is defined, or that the M is not 0. So we have to make it have to be stated that that's not 0. If it's continuous at M, or if f is continuous at m, then this limit would be approaching m. So then your answer would be whatever your limit is at f of m. And it's continuous there, and that means I know that it has to be the y value there. So if I didn't know it was continuous, I couldn't have concluded that. All right, so let's look at some of these things. So 2, so the limit as x approaches 7 is just going to be 7. X is 2, so we're going to be going to 2. So this is going to be 5 times the limit is f goes to 2, which is 12. So we have 5 times 12. This is the limit of 2, adding the 2. So 12 plus my -3. We're going to divide the 2 as long as they're not a 0, so they're good. So 12 divided by -3. We're going to raise it to a power of 4. So you're going to have -3 to a power of 4. This is the square root of the limit. So as we get to 2, it's 12, so it'd be square root of 12. And then f of g of x, so this is -3, and now you know what is f doing at -3? It's defined, so it's going to be a 5 there. So I use this property right here. Sorry, I didn't realize you guys couldn't see it. So I said that g, so I did the inside first, which was g, so g was -3, so then I plugged in -3 for the f, and it tells me that that's 5. So properties here, so a lot of times you can just plug in the value right there to see what you get out. So we're going to get, so what I'm saying is you're going to do 3 squared minus 4 times 3 plus 5. So our limit is 2. But sometimes you can't always, you can't just do direct substitution sometimes. So if I put this one in here, I'm going to have cosine of 0 over e, and that's in, what would be e to 0? E to a -0. So really that would be e to a 0. So that would be, I don't know, that one doesn't work. I have to think about that one. Because that should just be a 1 over 1. This one right here, when I plug in 4 down here, I'm going to get undefined. So I get 12 over 0. That's undefined. I plug in 3 here. Oh, this one says it can be evaluated. Sorry. I misread the directions up here. So this is just 1 over 1, so it's 1. I thought it was they're all supposed to be undefined. That one's undefined because it's 12 over 0. Plug in 3 here. I get 9 minus 5 over, so I get 4/6 or 2/3. So sometimes we can just plug the number in. That's great. Sometimes it doesn't work. When I plug in 2 here, I'm going to get 0 over 0. Anytime you get 0 over 0, then something else is going to happen, and we learn that in the next lesson. But you could look at the graph of this, and as we look at the graph, as we approach 2 from the left and the right, our y value is actually approaching 4. So this limit really equals 4, not 0 over 0. These brackets around the 0 is a greatest step function. So it's a step function where you take on the integer right here. So if I want to know as we're approaching 2, if I approach 2 from this direction, I'm approaching 1. In this direction, I'm approaching 2. So this one would not exist. So if I look at the graph of this one right here, the limit is x approaches 1. So if I approach 1 here, I'm getting 1, and from this side, I'm getting 1. So both of these y values are 1, so this could equal 1 here. Now let's see what happens when we get a 4. 4 from this side equals 2. 4 from this side equals 1. Those aren't the same. So this one would be does not exist.